So good morning, everybody. So I'll talk about stochastic optimal control, and I think my talk actually will sort of have the similar structure as Professor Boca's talk. So I will first talk about the results in Markov decision process, and then extend that to the continuous time model in controlled Markov diffusions. So I guess everyone here knows that it is challenging to solve Markov decision process and control the Markov diffusions due to the so-called curse of dimensionality. So many approximation methods have been developed to solve these problems, and many of these approximation methods have theoretical convergence results. But in practice, actually, it is really hard to judge the quality of a numerical solution. For example, it's really hard to tell how far the approximate value function is away from the true value function, right? So these two difficulties, that is, the difficulty to solve the problem and then the difficulty to judge the quality of an approximate solution, can be potentially relieved by the duality in these problems. So it's just some promise. It's not like saying the duality can completely solve these difficulties, but it provides some complementary way to relieve these difficulties. So the duality is based on the idea of information relaxation. I will talk about this in more detail later, but I just want to here address the two difficulties. So the dual problem, or the dual formulation, in fact, reduces to a sample pathwise optimization problem. So what it means is that we can simulate a sample path of the randomness in the system, and then given such a sample path, the problem becomes a deterministic optimization problem, which is much easier to solve. So we can do that for many sample paths and then average them to get an approximate value function. And then second, given a suboptimal solution or a policy, we can evaluate the dual bound based on the dual formulation. So then the duality gap between, associated with this optimal solution gives us a direct indication of the quality of the solution. The smaller the gap, then the closer the solution is to the optimal. But it's not, the opposite case is not necessarily true. Basically, what I mean is that it's not necessarily true that the larger the gap, the worse the optimal solution, the worse the approximate solution is. Why is that? I will explain that later in the numerical experiments, actually. So for this idea of duality by information relaxation, as far as we know, at least dates back to the early 90s. There are several papers by Davis and his co-authors on both the continuous time and the discrete time models, but they use a Lagrangian approach. And later, actually after these papers, it seems like there's not much attention following up these papers. I don't know why. I think it's probably these papers are quite technical to me, not to you. Definitely not to Zhou. So these papers are technical, and they also don't have computational methods. So maybe that's why there's not too much follow-up. But then this idea is revived again in recent years. There's a paper by Rogers in 2007 in the Siam Journal on Control Optimization. And then by Brown et al. In 2010 in Operations Research. So these two papers mostly focus on the discrete time model, the Markov decision process, and they put more emphasis on the computational benefits, computational side of this duality. And their approach can be viewed as a more general framework of the Davis approach. The Davis approach is basically a Lagrangian approach. And I would also like to mention that the idea of information relaxation has also been studied a long time ago in the community of stochastic programming by Rockefeller and Watson in the 1970s. So So in following, I first give you the problem formulation. We consider finite horizon problems. And then I will review the duality results in Markov decision processes, and then extend these results to controlled Markov diffusions, and then show you an application problem. So I guess everybody is very familiar with the problem formulation, but I'll still just quickly go through the setting here. So here, this is the Markov decision process. Xk is the state, Ak is the control, and Vk is the randomness or disturbance. So each Vk is a random vector. And then this equation describes how the state evolves. So our goal, or the goal of a decision maker, is to maximize the expected total cost, maximize the expected total reward over k time horizons. And the optimization is done over by picking an optimal control over the set AG. So AG here is the set of admissible controls that are adapted to the filtration G generated by VK. Professor Boca also mentioned this kind of control is called the non-anticipative control. So basically what it means is that the control can only depend on the past information, or the realizations of the past randomness. It cannot depend on the future, because we cannot use such a control in reality, right? Because in reality we cannot predict the future. Well, of course, unless you have some supernatural power, but most people cannot do that. So then in the continuous time model, here we consider the controlled Markov diffusions. So here UT is the control, and then WT is the Brownian motion. So we have the same goal to maximize the expected total reward. And here this set UF is a set of admissible controls that are progressively measurable to the filtration generated by the Brownian motion. So it has the same implication. The control needs to depend on the past. So in principle, these two problems can be solved based on the Bellman's principle, and the MDP can be solved by the dynamic programming iteration, and then the controlled Markov diffusions can be solved by the HJB equation, but these are only in principle, because you can see here this is basically a series of nested stochastic optimization in DP, and then HJB equation is a second order nonlinear partial differential equation. So numerical solution to these are hard, and they suffers from the curse of dimensionality. Okay. So because of that, so many approximation methods, like what they call approximate dynamic programming methods, have been proposed to solve the Bellman equation, or the dynamic programming. And then using these approximation methods, we will get an approximate solution. Basically, it's a suboptimal policy, right? So if we look at, the reward generated by a suboptimal policy gives us an lower bound on the value function. By the way, I should mention, just in case, so the VKs are called value function. So such a suboptimal policy will generate a lower bound on the value function. And in implementation, we can just simulate the states under such a suboptimal policy, and get the rewards and average that over many sample paths, and get such an estimate for the lower bound. And as I mentioned before, the quality of such a suboptimal policy or solution is hard to evaluate in practice. So it would be nice if we can get also an associated upper bound on the value function. And the idea of Rogers and Brown-Ito is basically, so they relax the constraint on the non-anticipative control. That is to allow the control to see the future, but then this access to the future information will be penalized by a certain function here, m. So here, notice this set A is not a AG, it's different. So it's A. This is a set of all the controls with AK in the, basically that's the position constraint for AK. So that means that we relax the constraint that the control has to be non-anticipative, and allow it to get access to the future information. And then this penalty function m, we say it is a feasible penalty function if it satisfies this condition. So this condition basically means that the penalty will not penalize a non-anticipative control, right? This is because that is a control we can use. So we want to choose this penalty function appropriately, so to put down this reward to get it close to the true value function. And just for the notation concern, we denote the set of feasible penalty functions by mg. So obviously here one trivial penalty is the zero penalty. We can just let this m to be equal to 0, then it satisfies this condition. And also it's easy to see this Lm now is bigger than or equal to the value function, right? Because the value function is just, this expression by taking out the superamount outside the expectation over the set Ag. So it's easy to show that this is an upper bound. But this upper bound could be very loose because the penalty is really dumb. It does not penalize anything, right? So the question is that, so how can we have a better penalty function, and what's the limit of this? So what's the best we can do? And then the weak duality results here says that actually for any feasible penalty function, this is an upper bound on the value function. So we just need to search within the set of feasible penalty functions. And then the strong duality result says that the infimum of Lm, so basically the smallest upper bound, actually coincides with the true value function. Okay, so this infimum can be actually achieved by, for example, by this so-called value function-based penalty, m star taking this form. And if you look at this expression a little bit closer, you can notice that delta v is the difference between the value function and the expected or the predicted value function based on the previous information. Okay, so that is kind of, you can intuitively understand that as the randomness part in the evolution of the value function. So this is just one penalty function that can achieve the strong duality. Actually, there are more. At least we know another one, which people call it as a gradient-based penalty. And in fact, their work can be interpreted as a gradient-based penalty, but I'm not going to the detail into this. So anyway, let's just focus on the value function-based penalty. And so this penalty is not directly usable because you can see it depends on the value function itself, which is the thing that we want to solve for at the beginning. But it gives us a guide on how to choose a good penalty function. So let's say if we already use some approximation method to get a suboptimal solution v hat, and then we can replace this exact v by the approximate v hat and get this approximation for the optimal penalty. And intuitively, we would think that the better approximate value function we have, then the better penalty we have. But so far, we don't have. I don't think there's a rigorous quantitative statement on that. It's just heuristic. So we can use such an approximation scheme, and then this obviously you can show that the expectation of MV hat is 0. Both of them are 0. So it satisfies the condition. So they are both feasible penalties we can use. So using such an approximate penalty plugging into here, then according to the weak duality result, we have an upper bound, right? And this upper bound still needs to be estimated because there's this expectation here. So from the computational perspective, this is sample path-wise optimization problem, because we can first sample sample a trajectory or sequence of v, the random variables v, and given such a sample path of v, the optimization problem inside the expectation, which we call it an inner optimization problem. So this inner optimization problem is a deterministic problem, a deterministic optimization problem whose variables are just a0 to ak. And that can be solved usually much easier, than stochastic optimization problem. So, questions? Okay. Okay. Yeah. So actually, what we do this is that we can do that for several sample paths and then average them together. That would be an estimator of the upper bound. So both lower bound and upper bound, I'm not saying we get the exact, we only get Monte Carlo estimator for the upper and lower bound. And of course, the more we sample, then the closer we get to the bounds. Yeah. So from this, of course, you can think of there are two possible, maybe more than two. So let's talk about ways of generating dual bounds on the value function. So one way is, basically what I just talked about. So we start from the primal problem, which is the original MDP, and solve this original POMDP using some approximation method to get a suboptimal policy, which induces a lower bound. And then using the policy or the lower bound, we can construct a penalty, plug that into the dual formulation, and then you evaluate the dual formulation to get an upper bound, right? So that is we start from the primal problem. Of course, we can also start from the dual problem, and we can solve the dual problem to get an upper bound. But one question here is, how can we find a good penalty? That's basically is equivalent to say, how can we find a good dual solution? Okay, the solution to the dual problem. Well, actually, after these two papers, I mean the Rogers and Brown's papers, there are quite a few papers coming up in recent years. Just quite basically, the focus is on how to find a good penalty. Okay, so I'll talk about that later. So once we get an upper bound, then we can use the upper bound to generate a suboptimal policy, and then simulate under the suboptimal policy will give us a lower bound. So these are two directions. And you may think that probably there's also a third way, right? So what we are thinking is that we can do these two iteratively. So the hope is that iteratively we will improve the solution to both the dual problem and the primal problem, so to get better policy and better penalties iteratively. But we don't know how to do that exactly right now. So there's also a complementarity slackness that characterizes the relationship between the optimal control and the optimal penalty. Basically are the solutions, the optimal solutions to the dual and the primal problem. So it says that given the two solutions are feasible, then a sufficient and necessary condition for them to be optimal is that the expectation of the optimal penalty evaluated at the optimal control is 0, and then it also satisfies this expression. So if you look at the left-hand side of this expression a little bit closer, if M star and A star are optimal, so here X star is the trajectory under the of the state under the optimal control. So because this term here, the expectation is 0, so this term is gone, and what left here is just the value function, right? So that means the value function is equal to the right-hand side given the optimal penalty function. So the implication here is that if the penalty is optimal, then the decision maker will be satisfied with non-anticipative control, even if he or she is allowed to choose an anticipative control. Okay. So just to summarize the duality results for the discrete time MDP. So we have this formulation LM, and it provides an upper bound on the value function for any feasible penalty function. And then the strong duality is also achieved for some optimal penalty M star. And this dual formulation may be easier to evaluate due to the deterministic nature of the inner optimization problem. So then the question for us is that, so we thought, can we establish a similar dual framework for the continuous time stochastic optimal control problems? Well, the short answer is yes. We will focus on the controlled Markov diffusions, and we will derive such a dual formulation. And the way we derive it, as you will see very shortly, so I think that also gives us the guidance on how to derive the dual formulation for other continuous time models, such as, for example, a controlled jump diffusion process. So from the computational perspective, then the most important thing is the penalty function. So what is the structure of the optimal penalty function, and how can we approximate such a penalty function, right? And we will also give the explicit form of such an optimal penalty function and expose the connection of that penalty function with the one we just see for the discrete time problem. And then we will compare these penalty functions on application problem. Okay. So here's the formulation of the controlled Markov diffusion, and Professor Volka also just introduced. So, so basically, okay. So I just want to emphasize again, this control is a non-anticipative control. So following the previous framework, so to construct the dual formulation, we already have the recipe, right? That is first to relax the non-anticipative constraint on the control and then penalize that. But the problem here is that if the control is anticipative, how can we define a solution to this SDE, right? So an anticipative control here is basically a control in the set U, the set of measurable U-value controls. So this is similar to the set of all the controls in the discrete time problem, and it has the same implication. It can depend on the future information. And then luckily, we found results in Davis and Bernstein paper. So they based on what they call the anticipating stochastic calculus. So given such a control, anticipative control, under some technical conditions, then we can define such a, so the equation 1, this SDE, actually admits a unique pathwise solution xt given such a control. Okay, so at least this is well defined if we look at the inner optimization problem. And then from that, we also similarly define the feasible penalty function h that should satisfy this condition, and it means that so it means that the penalty will not penalize any non-anticipative control. And then define LH. So this is, here you can see it's just in exactly a parallel way. So we define this LH, and then the penalty where h is the penalty function, and then the weak duality, we also have the weak duality result. So for any penalty function, then we have a upper bound on the value function, and then we also have the strong duality result. Okay, so the question is whether what h we can choose here to achieve this strong duality. Well, there is a trivial optimal penalty, h star here, and you can see here if you plug in this h star into LH, then these two terms are canceled out, and what left here is just the value function, right? So this is trivially holds, and we have this strong duality. But this trivial optimal penalty is not usable, not just because this V is what we want to solve, but also because even we use an approximation for this V, for this value function lower bound, then this approximate penalty function does not satisfy this condition. Okay, so it's not a feasible penalty. We cannot use it. Then we wonder, what is the corresponding value function-based penalty here in this continuous time model? Well, so the motivation for us here is to start from the trivial optimal penalty, but then explore the relationship between the optimal H penalty and the optimal control. So let's plug in the optimal U here, the optimal control here into the trivial trivial penalty function, optimal penalty function. And notice here, this is the reward, the final reward at time t, and that is equal to the value function at time t, okay? So we can plug in this, and then we can apply Ito's rule on this value function v of t. And that will give us the second line here. And notice here, this is the U star is the optimal control, so it satisfies the HJB equation. So this integrand here is equal to 0 for every t. So the first integral is just vanishes, it's 0, and what left here is this term, okay? So notice this is for optimal U. So from this observation, we sort of guess, we conjecture the optimal penalty H for any U is just taken this form, but with xt star replaced by just xt associated with the ut. But the problem here is that this is an Ito integral, so it is not well defined if ut is not adapted to the futuration. In fact, we can show that when U is in UF is in, so when U is a non-anticipative control, the optimal penalty function is indeed taking this form. But when U is not in UF, it actually has more complicated expressions, and we use Stochastic integral here. And so, but I'm not showing this complicated expression here. Just focus on this one here for U for the non-anticipative control. So the similar
Stochastic or Skorokhov?
Stochastic.
But that you also need non-anticipative for that.
No, we can. Okay. So we look at some results. So we basically based on some results in the Davis and Bernstein paper, and they can decompose the solution. Use some, so basically they decompose the solution to as like the solution to an SDE that and without control, and then to an ODE that with the control. So then, so then they can avoid this problem. So the intuition here is that this, so we can let's look at here, right? So if we take the expectation of these first two terms, then they are exactly the value function, right? If we take the expectation of these two terms, so that means this difference is basically the difference between the value function, the random variable, and then its expectation. So it can be understood as offsetting the randomness in the inner optimization problem, or as before, it offsets the randomness in the evolution. If you look at each term here, it's sort of as offsetting the randomness in the evolution of the value function. So that's what we think is, for other continuous time controlled problems, we can follow the same procedure here. We just need to apply the Ito's rule here. For example, if there's a jump, we apply the Ito's rule for the jump process here, and then we will get some expression, and we can conjecture, that would be the optimal penalty function, and further verify it. So that's why we believe that can be also generalized to other continuous time problems. And then here, this value function-based penalty is actually usable because we can replace this Vx, which is the partial derivative of V with respect to x, and then replace that by an approximation Vx hat. Notice also this is for an anticipative control. So this is for well, this is, I mean, theoretical results, but in numerical result experiments, we can always, we can also try to use such an approximation, even though it may not satisfy that you may not be non-anticipative, right? So this approximation here, so because these are two integrals, so the expectation of them are 0, so this one is a feasible penalty. And then we also have the complementarity slackness result, which has the same interpretation. Basically, if the penalty function is optimal, then an optimal non-anticipative control will be good enough, even if we are allowed to choose anticipative ones. So here's a summary of the due formulation for the discrete time MDP and then the continuous time control Markov diffusions. So we think the first three results are really straightforward extension, but the interesting thing is the value function based penalty here. And both have the same interpretations as I just mentioned. And we can also sort of compare and look at the gradient-based penalty, optimal penalty here, which I didn't list. Okay, so then next I want to show you how we can use these penalty functions in a numerical example. And actually the numerical example I will to solve is an MDP problem, so it's a discrete time problem. But we can show how we can also use this penalty function for the continuous model in a discrete problem and what benefit it can bring to us. Okay, so here we consider dynamic portfolio choice problem. So say there's a riskless asset such as a bank account, so it has a fixed return, and there are several risky assets such as stocks, so that give you stochastic returns, and you have a certain amount of money, so you want to decide how to invest to the riskless asset and the risky assets. And then you can also decide how much money to spend along the way. So first, this is a continuous time model, and phi here is the market state. So, for example, it could be denote the economy state or other factors that affect the market. And then WT is the wealth of the portfolio, so basically is the amount of money you have at time t. And the decision here is pi t, which is, so pi t here is the fraction of wealth invested in the risky asset, and the C tilde t is the rate of consumption, that is how fast you spend your money. So together, they are the control UT, okay? And they also satisfy some position constraints. For example, your consumption cannot exceed your wealth, and you cannot borrow money, such like this. These constraints. So the objective here is to maximize the expected utility of the intermediate consumption and the final wealth. There's a trade-off between these two terms because the more you spend in the middle, then in the expectation sense, you will have less money left in the end, right? And vice versa. So we need to find the optimal trade-off on the consumption and the investment, and also on how to invest the money. So here, UF is the set of non-anticipated control strategies subject to the position constraints, and the utility functions is this power function, which is non-decreasing, concave, and differentiable. So it's basically a risk-averse utility. And in practice, people usually decide, how their investment at discrete times. So people usually look at the discrete time model. So here we look at the discrete time model that is a discretization of the previous continuous time model with a time step delta. So these are just the discrete time model. And here, these Z tilde and Z are standard Gaussian random variables. So they are the randomness in the state, and then here AK is the control. So our goal here is try to estimate the expected utility H0 induced by a suboptimal policy, and then in order to know, how to tell how good this estimation is, then we are going also to derive an upper bound on the expected utility based on the dual approach. So again, here is the objective function or the value function. So to get a lower bound on the value function, we discretize the state and then apply dynamic programming and then use linear interpolation between the grid points to get the approximate value function and the approximate policy. So that is something just standard, not very interesting. But then to get the upper bound on the value function, we use the dual formulation. So here M is the penalty function, which is a function on the control A and then the two randomness, Z and Z tilde, right? So the first approach, since this is a discrete time problem, then of course you will probably think first, I will use the penalty, the value function based penalty for the MDP, right? So this is the first approach, and this is the, if you remember, this is basically the penalty, optimal value function based penalty for the MDP. So here is the value function, and here is the expected projected value function based on the previous state. And so we can use this, but then the problem is that in terms of computation, there's a conditional expectation here. So that means to estimate this conditional expectation, we need to simulate sub-sample path within a sample path. So if we already have a sample path for the states phi k and wk, then at this grid point we need to simulate several more subsample paths forward to estimate this conditional expectation. So this is often called nested simulation or simulation within simulation. So it's quite time consuming and does not give you such a very good results unless you have a very large sample size. And furthermore, so this utility function, we notice this utility function is concave. So, for a concave function, we can solve the optimization problem relatively easily using a lot of the existing solvers. But once we have this penalty function, because of the structure here, the inner optimization problem may not be concave anymore. So even though it's still deterministic optimization, then it may have multiple, local optimal solutions may be harder to solve. So then we take an alternative approach, that is to use the value function based penalty for the continuous model that we developed, and then discretize that penalty to get a penalty for this discrete problem. So the step one is just to plug in the expressions for the optimal value function based penalty for the continuous time model, and then we discretize this Ito integral here to get a penalty M2. Okay. Also, I omitted the expression here, but we can show that this M2 is a feasible penalty. It basically satisfies these conditions. It doesn't penalize any non-anticipative control. And then in terms of the computational efficiency, that is the point here. So this M2 is much better than the first one, M1, we try to use. So the M2 is in fact affine in A. So if we plug into here, then this inner optimization problem will still be concave. So that can be solved easily. And then furthermore, there's no conditional expectations in M2. So we don't have to do the nested simulation. Okay. So computationally, it's much easier. Do I have time? So, some time. Okay. Yeah, okay, so probably I'm the only one here talking about numerical results. Kind of, so other people are other presentations are more, theoretical. I'm just looking at the, play with the numbers here. So here, the numerical experiments, we talk about, just one market state variable and then 3 dimension of risky assets and some other parameter settings. So here, the value here, so each entry is the sample average of 10 independent runs, and then the standard error of the 10 independent runs is given in the parentheses. So the value is so the value is basically our estimator for the value function, and CE here denotes a certainty equivalent of the value function. Okay, so I will talk that. And the lower bound, the first column here is lower bound. Lower bound, we basically so we solve that. We solve the original problem to get a suboptimal policy A hat, and then we generate 100 random sequences of the sample path of the randomness, and then simulate under this suboptimal policy to generate 100 random sequences. So get an estimator for the lower bound, and the upper bound we use our penalty function, the second penalty function, and then generate 30 random sequences. So solve the inner optimization problem to get an estimator for the value. And zero penalty is, we let the penalty to be equal to 0, and then also that gets an upper bound. A lot of the existing so the certainty equivalent is but once we have this penalty function, because of the structure here, utility denoted by optimization problem may not be concave anymore. Even though it's still deterministic optimization, then it may have multiple basically local optimal solutions may be harder to solve. Reverse the effect of the utility function. An alternative approach that is to use the value function based penalty for the continuous model as a fraction that we developed, and then discretize that penalty. Okay, let's look at the results here. To get one, so if you look at the zero penalty, this discrete problem. So the upper bound one is just to plug in with respect to the lower bound and compare that with this lower bound. You can see the duality penalty for the continuous time model due to the zero penalty. And then we discretize this Ito integral here to get a penalty M2 as just we expected. Also, I omitted the expression here. But we can show that this M2 is a feasible penalty. Basically, satisfy this condition in the utility. It doesn't penalize any non-anticipative control. The duality in terms of the computational efficiency, that is the point here. So this M2 is much better than optimal. The first one, and we cannot say that. So when the duality gap is large, we cannot say that. So if we plug into here, then this inner optimization problem will still be concave, because so that can be solved easily. And then furthermore, there's no conditional expectation due to the suboptimality so we don't have to do the nested simulation, right? Because we also approximate it's much easier penalty function. So it could be the case that the approximation of the penalty is not very good. Yeah, okay, so we have a loose upper. Probably I'm the only one here talking about numerical duality gap here. So other people are very increase of the value in the duality gap in the value here. Just looking at we think it's because this is the power function which has this negative power, which is very sensitive to the solution of the inner optimization problem. So if in the inner optimization problem we don't have very precise approximation of the optimal penalty, then that small small approximation error will be amplified. So each entry so in the end we will have a large duality gap here. 10 independent runs. But if we look at the certainty equivalent, independent runs is given in the parentheses. Sort of reverse the utility function, right? This duality gap remains so the value is basically a relatively constant for the different values of gamma. And C here denotes in that certainty equivalent of the value function. We have reasonably good. And the lower bound, the first column here is lower solutions for the bound. We basically and for the penalty. So we solve that. We solve the original problem to get in conclusion. We establish a dual formulation for control mark of diffusion based on information relaxation of the sample path of the randomness and upper bound on the value function in practice. Simulated under the suboptimal policy to generate 100 random sequences. So get an estimator for the lower bound compactly as an Ito integral. We use under the natural free penalty function generated by the Brownian penalty function for non-anticipative control. Generate 30 random sequences, so solve the inner optimization problem to get from the numerical experiments is that and
the
zero
penalty should be chosen in a way
the penalty to be
to,
equal to 0.
by thinking about both its effectiveness and computational efficiency. So we want the penalty to be
so the certainty
near as
equivalent
optimal as possible, but we also want
the
computationally
of the
expected utility denoted by
is
easier to solve. Okay, so there's a trade-off here.
And I think there's a lot of opportunities
in the literature.
People
Along
often
line,
use the CE
in terms
to
of the
look at
computation,
basically which
methods.
is like to sort of to reverse the effect of the utility function. And then the duality gap here is the difference between the lower and upper bounds as a fraction of the lower bounds. So look at the results. Okay, let's look at the results here. So if you look at the zero penalty, the upper bound due to the zero penalty with respect to the lower bound, and compare that with this lower bound, you can see the duality gap here is much larger due to the zero penalty. So that induces loose upper bound as just we expected. And then the duality gap here are generally smaller when gamma is small. So gamma is basically the exponent in the utility function. When the duality gap here is small, that implies both the approximate policy and the approximate penalty are near optimal. However, we cannot say that, when the duality gap is large, we cannot say that the approximate policy is far away from the optimal one, because the
Yes, right?
okay, because the gap are due to the suboptimality of both the policy and the penalty, right? Because we also approximate the penalty function. So it could be the case that the approximation of the penalty is not very good. So we have a loose upper, a big duality gap here, and the increase of the value in the duality gap in the value here, we think is because this is the power function, which has this negative power, which is very sensitive to the solution of the inner optimization problem. So if in the inner optimization problem we don't have very precise approximation of the optimal penalty, then that small approximation error will be amplified. So in the end, we will have a large duality gap here. But if we look at the certainty equivalence, that's sort of reverse the utility function, right? This duality gap remains mostly constant, relatively constant for different values of gamma. Okay? So in that sense, we can still say that we have reasonably good solutions for the control and for the penalty.
Okay, good.
So in conclusion, we established a dual formulation for control Markov diffusions based on information relaxation, and it can be used to derive an upper bound on the value function in practice. And we also show this value function based optimal penalty can be written compactly as an Ito integral under the natural optimal value function generated by the Brownian motions for non-anticipative control.
It's simulation in the sense we simulate the sample path of the randomness in the problem.
Is that
it doesn't mean that we
should be chosen in a way to thinking about both its effectiveness and computational efficiency. So we want the penalty to be near as optimal as possible, but we also want computationally the inner optimization problem is easier to solve.
Okay. Well, so for a particular sample path, we are right. We know the future. We can know the solution. But the problem itself, you see, we want to look at the expected value. Maximize the expected reward. So unless I do an infinite number of sample paths, then I will be able to know the exact solution. Otherwise, I won't be able to know it, right? And actually, even infinite number of sample paths, I won't be able to know it because I don't have the optimal penalty function here, the exact optimal penalty function here. So. Yeah, so basically, right. I don't know if I answered your question. Right. Okay.
So when you do the primal and then you start with primal and then you start with dual. And then you mentioned something about doing both, but you said you don't know how to do it.
Oh, okay.
You don't know how to do it in terms of how to put them together, that it works? Or what is the challenge?
Okay, the challenge basically here is that we don't have some sort of like a monotonicity results, right? So we don't know whether an improved policy will definitely give us an improved penalty, and if we use an improved penalty, we'll definitely generate an improved. I mean, what do you mean? Yeah. So we don't know like how to.
That's what I thought you were going to do.
Try that.
I guess that.
We didn't seriously try it.
It works in discrete time. So
in this way. So because in discrete time. I don't think. Well, I don't think it's not. It doesn't hold. It's just like we don't know what is an exact definition here. How to rigorously define what is an improved penalty, in what sense, and how does the improved penalty affect the solution, and also in the other direction. So I don't have
it's not
too many results on this right now. We are thinking about the generator. Just not I just don't know how to how to explain that right now. We just have very rough idea. Optimal stopping. Actually, there is a paper on. So they look at what they call the multiplicative martingale and then the additive martingale penalty. So they actually can show the one improved multiplicative penalty can lead to an improved additive. So they can do this iteration among the multiplicative and the additive martingale penalties. So they can do this. I don't know what's the analogy here. You mean, well, we don't know the optimal value function in this problem.
But as I said, it's a simulation, right?
Well, it's simulation in the sense we simulate the sample path of the randomness in the problem. It doesn't mean that we have.
So she cannot simulate all.
Right. We cannot. I mean, this is still, this is still problem.
What I'm saying is you know the future.
Right. I know the future.
You know the future, so you can kind of solve.
Okay.
When you do the simulation, you are running that in a computer too.
Okay. Well, so for a particular sample path, you are right. We know the future. We can know the solution. But the problem itself, you see, we want to look at the expected value, maximize the expected reward. So unless I do an infinite number of sample paths, then I will be able to know the exact solution. Otherwise, I won't be able to know it, right? And actually, even infinite number of sample paths, I won't be able to know it because I don't have the optimal penalty function here, the exact optimal penalty function here. So, so basically, I don't know if I answered your question.
That's fine.
Okay.
So when you do the primal and then you started with primal and then you started with dual, and then you mentioned something about doing both, but you said we don't know how to do it. You don't know how to do it in terms of how to put them together, that it works, or what is the challenge? Okay, the challenge basically here is that we don't have some sort of like a monotonicity results, right? So we don't know whether an improved policy will definitely give us an improved penalty, and if we use an improved penalty, we'll definitely generate an improved. I mean, what do you mean? Yeah. So we don't know like how to. Just
numerically. Try that.
I guess that.
We didn't seriously try it. For in this way. So because
you strongly believe the monotonicity won't hold, so it's not worth it.
I don't think. Well, I don't think it's not. It doesn't hold. It's just like we don't know what is an exact definition here. How to rigorously define what is an improved penalty, in what sense, and how does the improved penalty affect the solution, and also in the other direction. So
yeah, I don't have too many results on this right now. We are thinking about something, but just not. Yeah, I just don't know how to. How to explain that right now. We just have very rough idea.
Even in the much simpler case of optimal stopping, this is not known to my mind.
No, optimal stopping. Actually, there is a paper on. So they look at what they call the multiplicative martingale and then the additive martingale penalty. So they actually can show the one improved multiplicative penalty can lead to an improved additive. So they can do this iteration among the multiplicative and the additive martingale penalties. So they can do this. I don't know what's the analogy here.
Okay, well, let's continue the discussion over break. Okay,
yeah.
thank you.
Okay, thank you.